what's the slope, right? And so on the first graph, what's the slope way back here? 0, really small, not quite 0, but really small positive. Do we agree? It's not quite 0. It's not a really, really small positive number. Agree? Still really small positive numbers, but we start to get a little bigger, right? And bigger. And bigger. But then at some point in here, do you agree we start to get smaller again? And smaller and then 0? So we have kind of a almost 0, it gets bigger, then it gets smaller again, and when I get to 0, it's 0. Everyone agree? Now, am I drawing a perfect sketch? No. But it is something like that. How high this value goes, I don't know. I don't know what that slope is. But it gets bigger and then smaller again back to 0. I did go ahead and cross. Was that a correct move? Because what's the slope here? Negative. It's kind of a small negative, then it gets steeper and then smaller again. So another kind of the same thing except on the other side, and then this levels out. Any questions about that? Again, that is not perfect, but it looks something like that. And let's look at the next one. What is the slope way out here? Really big negative number. Everyone agree? Steep negative value. It keeps getting bigger and bigger. Something like this out here. I think that says -1. Can you see it better? This is -1. So at -1, what happens to the slope? It's 0. So I'm heading to 0, right? And then it's positive until 0. Agree? It's negative, 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 negative. And it levels off and becomes positive at -1, and it's positive all the way to 0, so kind of a any questions so far? What happens after 0? It's negative. Is it negative for very long? No, only to about 1, right? So it has to curve back up and be positive again. Does it make sense that a quartic would give us a cubic derivative? Really tiny positive, but then gets bigger and bigger and bigger and bigger and bigger and bigger and bigger positive as we go. Looks like the slope here might be about 1. So it kind of looks like a repeat graph. Would that make sense? What is the graph of that? Does it look like it could be a graph of e to the x? What's the derivative of e to the x? Okay, so this one's pretty yucky. Pretty steep positive. Everyone agree? So it starts out as a pretty steep positive value. At -4, that's where that value becomes 0. Does everyone agree? Like that. And then right after 4, from 4 to -2, is that what it is? You have a little better picture than I do. From 4 to -2, we are negative, but at -2, we become positive again. So we're going to have to turn back up. Okay. function, so maximum on the derivative. There's your background. 2. And 4, the other one. Decreasing, so it's like 4 and then increasing. Again, those sketches won't be perfect, but we can get a pretty good idea of what the derivative is based on just looking at slope. So that's one page of your notes. I'll have a few other examples. So, example number 2.
When it crossed the origin, why did you have a max?
Good question. So my function is increasing, like the slope here is positive, pretty steep, but it gets steeper and steeper, but at some point in here it starts to get less steep. At the point of the function where I change my gravity, it looks like that happens at about 0, but it changes from concave up to the other. So that point of inflection would be where I start to go back down.
So why did you do maybe like 2? A max of 2.
Well, this is, at 2 there is a maximum, which means the derivative is 0 at 2. Maximums on the derivative are points of inflection on the original. Which brings you to that notes page you have in your handout from Andy, comparing those. One thing I want to point out about this notes page, I'm not going to read it to you. You can read it later. It does a lot of comparisons. Like it says, points of inflection happen when the first derivative is a maximum or minimum. Things like that. What I do want you to know is this is not how you justify things. This is how you know things. You justify from definitions. If you want to say a point of inflection happens somewhere, you say the first derivative or the second derivative is 0 and changes signs. You know what I mean by that? So don't use this for justification. That's one mistake my classes last year made, so I want to point that out from the get-go. These are not justifications. These are for your brain. These are for you to go, oh, okay, that's going to be this and this. But to justify things, we want to go back to definitions. Because if you want to explain why something is what it is, you want to use the design value. Point of inflection is this. Okay, so given the graph of f prime provided below, answer the following questions. So this is not on your notes page anymore. The rest of that packet is your homework. So that front page is the notes page. The rest of it's homework. I just didn't want you to have to draw those graphs on that. No, it is not due tomorrow. It's due Monday. Due Monday. It does look a lot longer than it really is. If you'll look at, for example, page number 1, it's a matching. There are 2 matching problems on that whole page. Okay, so it looks worse than it is. In total, it looks like we've got 16 problems on here. So it's not that many problems, but it is. Tomorrow in class we're doing another activity. We're playing a card game. Where does f of x have a relative maximum? Anytime you are given a graph on an AP problem, the first thing I'm going to ask myself is, what is this the graph of? Go read. What is this the graph of? The derivative. How do you know that? It says it is. It says f prime is. So I'm going to mental note that. One of the biggest mistakes people make on AP problems is using a graph as the wrong information. So this is f prime. If I am looking for relative maxes and mins on the original function, where on f prime do I look? To zeros. Does everyone agree? With zeros are where I will have maxes and mins. Now we could draw a sign chart. The first day I did one of these, I drew a sign chart here. Can you do that? Yeah. You can if you want to. Do you have to? Probably not. So let's look. This is 1, 2, 3. 3.5? Negative 3.5. So maximum or a minimum? And how do you know? Let's find out. Let's find out. To the left, what's the derivative? To the right, what's the derivative? Okay, quick little sign chart. The derivative is positive and negative. What is it? The maximum? Everyone agree? So you got to think about that. Even if you don't draw a sign chart, you think, okay, the derivative changed from positive to negative. So I have a relative max. Can you draw a sign chart? You need to draw it? Should you draw it? Yes, don't get it wrong. You need to draw a sign chart. Draw a sign chart. So at x equals, when I'm going to put approximately, we don't know it's exactly -3.5. We're guessing based on the picture. We have a relative maximum. Now let's talk about justification. How would we justify? So this is the thing we don't like to hear them ask on the AP exam, right? We don't like to hear justify, but we have to do it. And that prime equals 0, I like that. F prime -3.5 0. Is that enough? No. And what else? And F prime changes from positive to negative at that point. So that's what we did in our head. We just have to put that on paper. I want to overemphasize that will not grade your sign chart, even though your sign chart says that. You have to put that in words. Now the words you use can be, I didn't use full sentences and exact punctuation. That's okay, but you do have to put it in words.
How do you know it was negative?
So at -3.5, the derivative changes from positive to negative. Okay, what does the derivative change from over here? So what is that?
So that's like an FB.
This B. Good. So at 3.5 we have a relative minimum. Does everyone agree? Because the derivative changes from negative to positive. Why? Enough? Questions about that? So make sure you pay attention to those justifications. Now we didn't say by the first derivative test. You don't have to, but that is what we use. We use the first derivative test there. So we used a definition or theorem, not just a way to remember. Then what about a point of inflection? Oh, I've got to think. When do points of inflection happen?
When the prime 0.
When the second derivative, right, is 0, and, or undefined, and changes signs, right? The second derivative has to be 0 and changes signs. Well, what am I going to look at on the first derivative for the second derivative? The slope, right? And the max and the mins will be the place where the slope changes signs. will notice on that sheet that it says those are going to happen at maxes and mins on the first derivative. But we're not going to use that to justify, because that's not the definition of a point of inflection. So we're going to say if x is negative 2.5, 0, and 2.5. Again, if you put 2, that's great, or 2.25. Sure, whatever you think. We're not going to argue about that. Why? You could say a lot, but I'm going to say the slope of f prime is f double prime, right? The slope of f prime is the second derivative. And what am I going to say about the second derivative? F prime, or f double prime, depending on how you want to word it. F prime slope changes signs at negative 2.5, 0, and 2.5. Or you could say f double prime changes signs at negative 2.5, 0, and 2.5. Remember though, make sure you use the definition. Don't use, there's maximum or minimum. Yes, that's how you know. But why does that tell you it's a point of inflection? We go back to the definition. It's because the second derivative is 0 and changes signs at that point. I'd let the reader know how I know that. I said, I'm looking at the slope, right? Again, they also would have accepted after this statement saying f prime slope changes signs at those, so that would work as well. So you could put a little leeway in that. Just suppose f of 0 is negative 2. Sketch one possible graph for f of x. Why did they have to tell us that f of 0 is negative 2? For us to be able to go backwards. So we have to have a starting point. We know the slope. We know the slope of x squared, right? But that picture will look the derivative of x squared will look identical to x squared plus 10, x squared plus 100, x squared minus 50, right? Those all have the same derivative. So to go backwards, we need a point to start with. Does that make sense? So, thank you.
Sure.
F of 0 is negative 2. What do I know? Would it hurt you to sketch two sign charts to help you out? So we kind of did that up here, right? Negative 3.5. Positive. So they're increasing, decreasing, and increasing. Everyone agree? to negative, right? So over here I'm negative. In between here I'm positive. What about after 3? I'm still positive. So the second derivative only changes signs at negative 1. See that? These are all things you knew if we had an equation, but we're just looking at it graphically instead of equation, which is a little trickier. So where do we have a point of inflection? X equals negative 1. Why? And I heard someone say negative to positive. You can say that, or you can say change the signs. Both of those will work. What intervals are we trying to pick up? Negative 1 to infinity, or you could do negative 1 to 3 and 3 to infinity. Both of those would be perfect. They wouldn't. Both of those are great. Why? That's my justification. Second derivative is positive. So a lot of times when we hear the word justification, we get English in our brain and we think we got to write a paragraph. We don't have to write a paragraph. We just have to write a full mathematical thought. Is this a full mathematical thought? Second derivative is greater than 0. That means we're talking about. Go feel a little better about justifications after saying some things. Not terrible. We don't like them.
Okay, so since B is not the same as the first derivative, that's
Oh, and I should say, sorry.
well, not only that, but
Hold on.
okay.
Sorry. It's G, not F.
But if it's asking what interval is just G of X, don't get the negative 1 to 3 is off.
Okay.
Why choose?
Look. What is this graph of?
That's the second.
Okay. This is the second derivative. I want to know when G is talking about. That's when the second derivative is positive. So this is positive when it's above the x-axis. You see that? So remember, this is not G. On G, you would look at the shape, but this is not G. This is G double prime. So to look at G double prime and find concavity, we look at whether it's positive. And you might need to draw a sign chart.
Is that negative, like when below and positives are below?
That's right. And isn't that how you tell negative or positive from a graph? You don't look at